Greetings, fellow learners. Now, before we get into this wonderful world of artificial neurons, I have a thought-provoking question for you. Do you think that modern neural networks represent biological neural networks? Now, personally, I don't think this is the case. Models are at best simplified representations of a very complex biological process. But what do you think? Please comment down below and let me hear your thoughts. Now, this video is going to be divided into 3 passes where we're going to talk about computation models and why we need an artificial neuron. And then we're going to discuss the biological neuron, followed by the actual mathematical formulations of the artificial neuron itself. So it's going to be a lot of fun, so let's get to it. For this first pass, let's try to get an understanding of why the artificial neuron was created. So to do this, we go back to 1928 with the mathematician David Hilbert, who posited a question: does there exist a mechanical process to prove any mathematical statement as true or false? Now, Alan Turing took a stab at answering this question, and in order to do so, he first needed to define what is a mechanical process. And he defined this to be a sequence of steps that requires calculations or computations. And once he had this definition, he devised a Turing machine. A Turing machine is an abstract machine that, 1, it provided a framework for creating a mechanical process for a given complex problem, and 2, it proved the problem as either true or false if the problem was decidable or computable. And so, to answer this question that David Hilbert posited of whether there exists a mechanical process to prove any mathematical statement as true or false, Alan Turing replied with the negative, and specifically highlighting that there exists some mathematical statements or even problems in general that cannot simply be boiled down to an answer of either true or false, and these were considered undecidable. And one example of such a problem is like the halting problem. Something that's important to note here is this first point about the Turing machine. That is, the Turing machine provided a framework for creating a mechanical process for a given complex problem. Now, restated, or explicitly stated, the Turing machine provided a framework for solving complex problems by breaking them down into manageable steps that require computation. And now this was kind of the idea that was used by 2 people who were Walter Pitts and Warren McCulloch, one a logician and another a neurologist. Now, these 2 were interested in cognition and intelligence, and so they wanted to understand better biological neurons. Now, they made use of this statement, that is, that the Turing machine provided a framework for solving complex problems by breaking them down into manageable steps that require computation. And what they did was they took a complex biological neuron process and broke it down into manageable computation steps. And in doing this, they created a computation model of a biological neuron known as the artificial neuron. Quiz time! It's that time of video. Have you been paying attention? Let's quiz you to find out. Why was the artificial neuron created? A, to better understand the biological neuron. B, to better understand intelligence. C, to solve complex problems. Or D, to compete with the Turing machine. Note that multiple answers here may be correct, and I'll give you a few seconds to answer this question. The correct options are A and B, but can you tell me why? Give your reasoning down in the comments below and let's have a discussion. And if you like what you're seeing here, please do consider giving this video a thumbs up because it'll really help me a lot. Now, that's going to do it for quiz time and pass 1 of this video, but keep paying attention because I will be back to quiz you. In this pass, let's actually go through the workings of a biological neuron. Note that in the 1940s, not all of this information was known, but at least the high-level details of a rough outline were kind of known. So with that in mind, let's get to it. So we have this nerve cell over here, and it consists of dendrites, a cell body, which is the soma. Then it has an axon, as well as axon terminals. The myelin over here is a fatty substance that wraps around the axon. Now, how does this biological nerve cell actually carry a signal? So, first of all, the signal will be propagated from other cells that preceded it. So we have the axon terminals from other cells. There'll be hundreds and thousands of these. Now, at each of these intersection points of the axon terminals of the previous cell, as well as the dendrites of this current cell, they are known as a synapse. And if we kind of magnify this synapse, we can kind of see here is the axon terminal of the previous cell. Here is the current cell's dendrite. And we have these dots over here that represent neurotransmitters. These are like chemical messengers to transmit a chemical signal from one cell to the next. And then the dendrites over here consist of these tiny receptors, where when they come in contact with a neurotransmitter, there are ion channels within this nerve cell that will open up that allow the flow of positive or negative charges. So these could be like positive sodium ions or negative chloride ions. They can flow in and out of this cell over here. Now, if there is a net influx of the positive ions, then this means that there has been an excitatory postsynaptic potential. Postsynaptic here is on the side of the synapse of the output end, which is like the dendrite over here. Now, if there was a net influx of negative ions, however, in this dendrite, we would see that there is an inhibitory postsynaptic potential. Now, it is in this way that we have a chemical signal over here in the synapse converted into charged electrical signal. So let's actually get a better understanding now of the overall flow of how a signal is transmitted from one end of the neuron to the other. So first of all, we have this entire nerve cell that is sitting at a resting membrane potential of negative 70 millivolts. And when we say a resting membrane potential, it is the charge of the nerve cell minus the charge of the area surrounding the nerve cell. And that typically sits at negative 70 millivolts when there is no signal that's propagating through this nerve cell. Now, as a first step when transmitting a signal, we would have neurotransmitters that release from axon terminals of the previous neuron into the receptors of the dendrites over here. So that's our chemical signal. Next, this causes ion charges of whether it's sodium, calcium chloride to flow in and out of the neuron, changing its charge. And this could either be excitatory or inhibitory. Now, if the membrane's potential now crosses a certain threshold, that is over all of these individual synapse regions, if it crosses a certain threshold, which is typically negative 55 millivolts, this triggers an action potential, and an electrical signal will then be propagated through the axon. And when this happens, we say that this neuron has fired. Now, we have this myelin over here, which is a fatty substance that enables faster transmission of charge through the axon. And when the electrical signal reaches the axon terminals, this triggers the release of neurotransmitters, and the process then starts again for the next cells. So this is kind of the overall picture of how signals are propagated through a biological neuron. Quiz time! It's that time of video again. Have you been paying attention? Let's quiz you to find out. When does a neuron fire? A. After the difference in charge inside and outside the neuron exceeds some threshold. B. After the difference in charge inside and outside the neuron goes below some threshold. C. After the neurotransmitters enter the dendrites. Or D. after the axon carries an electrical signal. Note that multiple options here may be correct, and I'll give you a few seconds to answer this question. The correct option is A, but can you tell me why? Please give your reasoning down in the comments below and let's have a discussion. And that's going to do it for quiz 2 and pass 2 of this explanation, but keep paying attention because I will be back to quiz you. Now in this pass, let's actually talk about this artificial neuron. So we have McCulloch and Pitts who wanted to understand intelligence, and specifically so, they wanted to understand the intelligence that derives from a single biological neuron. Now, they kind of knew some of the complex signal processing of the neuron that we discussed in pass 2, but they had to make a lot of assumptions too. And what they were thinking here was that, well, let's break down this complex biological process into manageable computation steps, kind of how like Turing did back in the 1930s. And so they created what we call today the McCulloch-Pitts artificial neuron. So this artificial neuron is a computation model of a biological neuron designed to understand intelligence capabilities of said biological neuron. Now, model is a simplified representation of, well, a biological neuron, and computation model means that this simplified representation can be broken down to a set of steps that require just calculations in general. And we're going to take a look at those calculations and compare it to the actual biological process now moving forward. So here's the structure of the McCulloch-Pitts artificial neuron. We have a neuron that consists of inputs, weights, and outputs. So first of all, in the biological neuron, we mentioned that there is neurotransmitters released from axon terminals of the previous neuron into the receptors of the dendrites. Now, in the artificial neuron, this is represented through the inputs, where the inputs indicate signals from other neurons. So if, from the axon terminals, there was no signal from other neurons, we would say I over here, this I would be 0. But if there was signal, that is, there were like neurotransmitter signals that were received by the dendrites, then we would say that I is equal to 1, which indicates that like a signal has occurred or is input from the neurotransmitters from the previous cells. So these are essentially inputs from the previous neurons. Now, in the biological neuron case, this causes the ionic charge to flow in and out of the neuron, changing its charge, and this could be either excitatory or inhibitory. Now, this excitation and inhibition is kind of given by the weights. They represent the charge of the dendrite. So the weight W is equal to 1 exists if there is a net positive charge or there is an excitatory response. And W is equal to -1 if there is a net negative charge or an inhibitory response. So we have W1 and W2 can take different values of 1 or -1. Now, back to the biological neuron. Now, if the membrane potential crosses a certain threshold, this triggers an action potential, and then we say that the neuron has fired. Now, in our artificial neuron, the way that we represent this is that we have a membrane potential. This will be the sum of all of these weight products and input products over here. And then we'll have a threshold potential that is going to be T, some threshold. And we'll have an output, which will be a binary output that represents 1 if the neuron fires or 0 if the neuron does not fire. And we will determine this if, the membrane potential is greater than a threshold, the neuron fires. If the membrane potential is less than a threshold, it does not fire. And so we have boiled down a complex biological process into a sequence of calculations in a much simplified version of the biological neuron, and hence this is a computation model. Computation because of calculations, model because it's a simplified representation of the biological system. And so we have the McCulloch-Pitts artificial neuron. Now, one of the major pros here is that, this artificial neuron can perform propositional logic. And for example, what I mean by that is like we can actually create logic gates. So we can simulate an AND gate from just a single neuron. So if we set the threshold as 2 and the weights to be 1 and 1, then 2 inputs that are 0, this will be, well, we're going to have a sum of products, which is going to be 0. It's not greater than 2, and hence the output is 0. So 0 and 0 is 0. Similarly, 0 and 1 is 0. And then we have 1 and 0, and that's going to be 0. And 1 and 1 is 1. So it functions as a proper AND gate. Similarly, you can see that it functions as an OR gate too. In this case, we need to set the threshold to be 1. The weights remain the same as 1 and 1. So 0 or 0 becomes 0. 0 or 1 becomes 1. 1 or 0 becomes 1. And then 1 or 1 becomes 1 too. In a similar case, it also functions as a proper NOT gate. So let's say the threshold here now is 0, and the weight, there's only one weight, so it's -1 because there's only one input. We have 0 times -1, which is going to be 0, and it's greater than or equal to the threshold, hence it's 1. So input 0, output 1. Similarly, if the input is 1, the output will be 0. So interestingly enough, though, this is just a single neuron performing these operations. And we can even connect these single neurons to create a network of neurons, a neural network, in order to perform more complex logical operations, for example, like XOR. So each of these little things, whether it's AND or not, these are individual McCulloch-Pitts artificial neurons. Now, a con here, a major con, is that there is no effective learning procedure. So every single time that we have a neuron and we want to perform a certain process, we need to explicitly set the weights and the thresholds by hand. However, this is not how the brain works. The humans learn. And so if I were to summarize the entire thought process, the works and the conclusions of McCulloch and Pitts, it would go something like this. To understand human intelligence, we created a computation model of a biological neuron called the artificial neuron. A network of such neurons is capable of propositional logic. Now, while it is not clear that the complex biological neural networks perform logic in this way, it is a starting point. So, I hope all of this now makes sense. Quiz time. Ooh, this is going to be a fun one. Unlike a biological neuron, the McCulloch-Pitts neuron, A, can only accept binary inputs. B, has a concept of memory. C, cannot learn from data. Or D, is a computation model. Note that multiple options here may be correct, and I'll give you a few seconds to answer this question. The correct answers are A, C, and D. But can you tell me why? Give your reasoning down in the comments below and let's have a discussion. And if you do think I deserve it at this point, please do consider giving this video a like because it will help me out a lot. And that's going to do it for quiz time and pass 3 of this explanation. But before we go, let's generate a summary. So in this video, we started looking at the McCulloch-Pitts artificial neuron. And the artificial neuron is a computation model of a biological neuron designed to understand intelligence capability of said biological neuron. It's a model because it's a simplified representation, a computation model because we can break this down into a set of steps that are computable or calculatable. And so we established the relationship between a biological process of signal transmission and boiled it down to a set of mechanical steps right here for the artificial neuron. We then started talking about the pros of how it can function as logic gates and perform propositional logic, but also highlighted the con that there is no learning procedure and that this is not exactly how the brain works. And then we finished with our well-rounding statement that is, to understand human intelligence, the computation model, which is this artificial neuron, was created, and a network of neurons could perform propositional logic, but this is not necessarily indicative of this exactly is the way that the biological neural network actually performs logic. But it's a starting point. So I hope all of this made sense, and thank you all so much for watching. If you think I do deserve it, please do consider giving this video a like. It'll help me out a lot. And if you want to continue your AI journey, do click on this video right over here. You won't regret it, and I will see you in the next one. Bye-bye.